Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 7 on electrostatics, Coulomb's law. It says a small sphere R with a charge of negative 50 nanocoulombs is placed in a narrow cylindrical glass tube vertically above sphere S with a charge of negative 20 nanocoulombs. Sphere R is suspended from a light string secured to a beam as shown in the diagram. The mass of sphere S is twice the mass of sphere R. Ignore the effect of air friction. Right, so we have this here. They say both spheres come to equilibrium when the tension on the string is 8 Newton. Now, when it comes to equilibrium, we understand that the system here will be stationary, and then therefore the acceleration will have to be 0 meter per second square, so there is no movement there. 7.1.1 says state Coulomb's law in words. Right, so how do we state that? For 7.1.1, we say the magnitude of the electrostatic force, exerted by one point charge on another point charge is directly proportional to the product of the magnitudes, of their charges and inversely proportional to the square of the distance between them. All right. So for 2 marks, that's how we are supposed to define Coulomb's law. Right. And then we have 7.1.2. It says, draw a labeled free body diagram indicating all the forces acting on sphere R. Right. So how do we calculate the forces acting on sphere R? This is how we are supposed to do it. So for 3 marks, we know that we are supposed to have 3 forces. And then obviously the first one that will be acting downward as always is your gravitational force. And then right here, we can see that our string is up here. So this is our tension. But then what is that force now? You will soon realize that R is experiencing an electrostatic force, more specifically a repulsion electrostatic force from S, because both of them are negative charges. And then we know that like charges repel each other, right? So the electrostatic force experienced by R due to S will cause R to be repelled up, right? So we need to indicate that and say this is our electrostatic force. We indicate it as Fe. So now we have 3 forces. It's the tension force, and then the electrostatic force acting upward, and then the gravitational force is downward. Now 7.1.3 is saying calculate the mass of sphere S. So in this case, let's just choose that we'll take downward as positive, as we can see that as sphere R was being suspended down here. So we'll just take this one as positive, and all the forces going upward, we will take them as negative. Now, this is up to you. If you decide to take upward as positive and downward as negative, it's still one and the same thing, because here we are dealing with the spheres that are at equilibrium. So the acceleration will be equals to 0 meters per second square, which we do know at this case, when this is at equilibrium, it simply means that your upward forces will be balancing out the downward forces. So at the end of the day, what you have here will be equated to what you have down here, right? So it doesn't matter which direction you actually choose as your positive direction, right? Then now for 7.1.3, we are going to start by calculating the electrostatic force between sphere R and sphere S, right? Because we are on electrostatics and Coulomb's law, so definitely we have to calculate the electrostatic force there. So K is 9 times 10 to the exponent of positive 9. It's a constant. Your Q1, remember, when it comes to this formula, we don't substitute in the negative there. We are only focused on the magnitudes. That means the sizes. So this is 50 times 10 to the exponent of negative 9. And then as our Q2 will say, this is 20 times 10 to the exponent of negative 9. Now, what is the distance between the two spheres? Can see it is indicated 4 centimeters. But then again, we must remember our distance cannot be indicated in centimeters. It always has to be indicated in meters, m. So how do we convert centimeters to meters? We know that we have to divide by 100. Now, if we say 4 divided by 100, this is going to give us 0.04. And then square that. Remember, it's the square of the distance between the two point charges. Now, if you punch that into your calculator, it is supposed to give you, so let's quickly punch it into our calculator. We get 5.625 times 10 to the exponent of negative 3 newtons, right? So, okay, this is the electrostatic force between sphere S and R. But then here we are to calculate the mass. How are we going to calculate the mass? You can see that we just drew the free body diagram. So that means we have to borrow the concept of Newton's second law here, right? So F net is equals to ma. Now you always have to note the similarities between your Coulomb's law and your Newton's second law, right? So if in this formula here, if you can check it, it is still a bit similar to the one you use for universal gravitation law, right? Newton's gravitation law. Then F net is equals to ma. That's what we have. Now, from our free body diagram, we said we want to take downward as positive. So we had our Fg there, and then the forces that were acting upward, that was your tension and also your electrostatic force. And then this is equals to ma. Now, for Fg, we know that this breaks down to mass times the gravitational acceleration, which is mg. And then we have minus the tension. We were told that it is 8. So when the system comes to equilibrium, or when both spheres are at equilibrium, then this is 8. The electrostatic force we just calculated right now, so 5.625 times 10 to the exponent of negative 3. Now again, we don't have the mass, but our acceleration is 0 because the system is at equilibrium, right? Now here we have mass. The g here, which is the gravitational acceleration, the acceleration due to gravity, is 9.8. This is always a constant. Now, if you punch this into our calculator, what do we get? We get negative 8.0056. I'm just going to round off to at least 4 decimal places because it is not the final answer. Then the mass times 0 is 0 here. Then we can just take this over to that side. So on the left-hand side, we are left with 9.8 m, and then this is equals to positive 8.0056. Then to find our value for m, we can divide both sides by 9.8. And just like that now, our value for m, the mass, will be equals to what? 0.8169 kg. But then note that what we just calculated here is the mass, of sphere R, because this we were doing for sphere R. Remember, the electrostatic force that we were calculating here is the electrostatic force experienced by sphere R. So that means the mass that we just calculated here was for sphere R, and therefore we need to consider that they said sphere S. When we go back here, they said the mass of sphere S is twice the mass of sphere R, right? So if this is sphere R, then what should be the mass for sphere S? Now we do understand that it would have to be twice the sphere R. So this is that multiplied by 2. It is going to give us 1.63 kg, right? So note that that statement was very important there, to say the mass of the sphere is twice the mass of sphere R, right? So that's why we needed to come here and remember to multiply by 2, because what we initially got was the mass of sphere R. Now to get the mass of sphere S, we need to take the mass of sphere R and multiply it by 2, right? And then just like that, we have our 6 marks. So nice one there. So again, with the 6-mark question, you can see that we first needed to figure out what is the electrostatic force between R and S. And then from there on, we can now apply our knowledge of Newton's second law in order to come up with the mass. Okay, so let's proceed. We have now 7.2. It says 2-point charges Q1 and Q2 are placed 60 centimeter apart. So you always have to note this trend here with your question papers. With your 7.1, most of the cases, that's just your electrostatic force, whereby you have to use this formula, F is equals to K Q1 Q2 over R squared. But then when it comes to 7.2, in most of the cases, now you are dealing with the electric field, whereby you now have to use the formula E is equals to KQ over R squared. In most of the question papers, you will always note that that is the trend, right? So you need to know how to use these formulas here. Then we are given that charge Q1 carries positive 30 microcoulomb. Note this time it's not nanocoulomb, it's microcoulomb. And then as Q2 carries negative 90 microcoulomb, points A, B, and C along a straight line are positions in the electric field surrounding the charges. C is 5 centimeter from point charge Q2 as shown in the diagram below. Again, we can see that our distances are given in centimeters, which is not the desired SI unit. We still need to convert to meters. Now we have another definition, define the electric field at a point. So which is what you should note when it comes to electrostatic force, there are 2 definitions. It's Coulomb's law and electric field at a point. You might be asked those 2 definitions, or they might ask you one of the definitions, but then do not walk into the exam without knowing those 2 definitions. Okay, what is electric field at a point? We say this is the electrostatic force. The electrostatic force experienced per unit positive charge placed at that point. Placed at that point, right? So that electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So for 2 marks, that's how you define it exactly as it comes there. Then 7.2.2, explain why the net electric field is not 0 at positions B and C. So we must comment on each individual position here. Why is it not 0 at B? Why is it not 0 at C? Now, why is the electrostatic force at B not 0? Then for B, we are simply going to say, when we look at B there and we are looking at charges Q2 and Q1 and Q2, we can see that there, the field, note that this is always positive, right? And then Q1, we've been told that it is negative, and then Q2, we also been told that it is Q2, we are told that, okay, Q1 meant to say it's positive and Q2 is the one that is negative. Pardon me for that. Now, if we are to look at the electric field on B, so where it will experience the electric field in what direction, because it is being repelled by Q1. This is a positive and positive. We know that it will face this direction to the right because now it will experience a repulsion force from Q1. But then note that Q2 here is negative. So B, your point charge B, in reference to Q2, it will be attracted to Q2. So now we know that it is impossible to have your net electric field as zero if the electric fields are all in the same direction. So they're all going to the right. So that means it is impossible to have an electric field of zero, because in order for you to have an electric field of zero, you have to make sure that the electric fields are going in opposite directions. And going in opposite directions, and also they are equal in magnitude. So for example, if you have 20 Newton per Coulomb to the left and also 20 Newton per Coulomb to the right, then it is possible to have your E net being 0 newtons, because what will happen here is that the electric field strengths will cancel each other out. Okay, so now we are supposed to say for B, the field or the electric field from both charges are in the same direction, right? So that's the reason why in B we don't have a net electric field of zero. But then we just got 1 mark from that. Remember, we are still supposed to explain why is it not the case when it comes to C. Now, when it comes to C, it's pretty obvious. Q2 is much more closer to C than Q1 is, right? So Q1 is a bit far from point C than Q2 is. So obviously, in this case, Q2 would have to experience a much stronger electric field than Q1, since it is much closer to that. So for C, we are going to mention that C is closer. So C, we are talking about this point here, this point charge. So C is closer to Q2 than Q1. And then again, we can see that the charge Q2, let me indicate the way they indicated, we can see that the magnitude of the charge Q2 is greater than the magnitude of the charge Q1, which is also another factor here. The fact that their charges are not even equal. But then again, here we have the one that is a bigger charge being closer to the point charge there. So meaning that it will experience a stronger electric field, right? So, okay, that's how we were supposed to explain that. So this is a mark for explaining for B and another mark for explaining for C. So 2 marks. Then let's now check 7.2.3. It says A is 80 centimeter from point charge Q2. Calculate the net electric field at point A. Right. Now, A is the point charge, and then everything that we are calculating here must now be in reference to A, because we are being asked to calculate the net electric field at point A. So this is how we're going to have it. So we'll say, what is the distance between A to Q2? We've been told that it is 80 centimeters. So let's indicate it up here. So up until this point, this will be 80 centimeters. But then from here up until here, we've been told it's 60 centimeters, meaning what we have in here is just 20 centimeters, which now this would represent the distance between Q1 to point charge A. Remember, when calculating the electric field, it is always the charge to the point charge. So the charge to the point charge. So we have Q1 to the point charge A, and then we have Q2 to the point charge A. So everything is calculated in reference to the point charge. Okay, so now that means to indicate E1, I would say, okay, E1 would be represented by K Q1 over R squared. Then my K is 9 times 10 to the exponent of 9. The Q1 here, we are given it's 30 times 10 to the exponent of -6. Remember, microcoulomb. So whenever you're converting microcoulomb, it's always particular number multiplied by 10 to the exponent of -6. And nanocoulomb, it's a particular number multiplied by 10 to the exponent of -9. So always remember that as your necessary conversions for electrostatics. Then the distance from Q1 to point charge A is 20 centimeters, which we do understand we have to then divide by 100 so that we have the distance in meters. So this will give us 0.2. Then square that. Now, let's indicate the direction. Remember, in order to know about the direction, we have to first draw the free body diagram. So A here is a point charge, it's always positive. Q1 is also positive. So that means the direction of A due to Q1 will be to the left because it will be repelled. So this, let's indicate, will be E1, which is the electric field at A due to Q1. Then Q2 is negative, but then A remains positive. So because of the positive and negative, we understand that A will have to be attracted towards Q2. So this will be indicating E2, which is the electric field due to charge Q2. Now, okay, since we have that, we understand that this is to the left and that is to the right. We are calculating E1, right? So when we find the answer here, punch it into our calculator, we are getting 6,750,000 Newton per Coulomb. To which direction? To the left. To the left. And then let's now calculate E2. This is KQ2 over R squared. Again, our K is a constant, 9 times 10 to the exponent of 9. Our Q2 now is this, which we've been told it's 90 microcoulomb. Again, you don't substitute the negative into this formula. Over the distance from Q2 to A, we've been told it's 80 centimeters. So we're going to have our 80 divided by 100, which is 0.8. And then square. Now, if you punch that into your calculator, you get 1,265,625 Newton per Coulomb to the right. Now, if we say that we are choosing right as positive, if we are saying that we are choosing right as positive, that means this here would have to be indicated as a negative, and this here would have to be indicated as a positive. Now we can see that the fields are in opposite directions. And if the fields are in opposite directions, then in order to find our E net, we have to subtract. So this is E net is equals to E1 plus E2, right? But then we are aware that our E1 is a negative. So we have to say negative E1 plus E2. So this will become negative 6,750,000 plus 1,265,625. Then you simply just grab your calculator and punch all of that into your calculator. You get negative 5,484,375 Newton per Coulomb. Right. Now, since it came out as a negative, it simply means that the direction of the net electric field is to the left. So therefore, we conclude our E net is equals to 5,484,375 Newton per Coulomb. To which direction? To the left. Note that when I conclude here, I no longer put the negative, right? So the negative is now changed to the direction. Remember, your answers in physical science, you cannot leave them as negative. You need to conclude and tell us what the negative means. But then, of course, that's not the case when it comes to your work energy and power. If something is doing negative work, then it will have negative value. Right. So, okay, that's it with your question. So it was all for 21 marks. That's all you were supposed to do. And then go about this question. So you know what to do. Press the thumbs up button if you have enjoyed the lesson, then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please, please, please smash that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.